Good morning. Today we are going to deal with Bohr's atom model. We will start with the informations that we got from Rutherford's atom model. After the gold foil experiment, Rutherford proposed the planetary model of atom, and just like the solar system, the nucleus lies in the center of the atom and the electrons revolves around it in their orbits. Let's see what are the conclusions drawn by Rutherford after he done the alpha particle scattering experiment. Most of the space inside the atom is empty because most of the alpha particles passed through the gold foil without getting deflected. And very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. And a very small fraction of alpha particles were deflected by 180 degree, indicating that all the positive charges and mass of the gold atom were concentrated in a very small volume within that atom. So this is the picture showing the alpha scattering, in which most alpha particles go undeflected and a few alpha particles are slightly deflected and very few alpha particles bounce off. So from this analysis, Rutherford proposed the nuclear model of the atom, in which he described an atom as consisting of positively charged nucleus which is surrounded by electrons moving around it. Second point is that electrons and the nucleus are held together by coulombic force of attraction. We know that electrons are negatively charged and the nucleus is positively charged. So there is a coulombic force of attraction between them. And the third point is the size of the nucleus is very small as compared to the size of the atom. Here we can see that the radius of the nucleus is ranging from 10 raised to minus 14 to 10 raised to minus 15 meter, whereas the radius of an atom is 10 raised to minus 10 meter. So the size of the nucleus is about 10,000th part of the size of an atom. So the size of nucleus is very small as compared to the size of the atom. The next point he made is almost the entire mass of an atom is concentrated in its nucleus. And the last point, atom as a whole is electrically neutral. So the number of protons inside the nucleus of an atom and the number of electrons surrounding the nucleus are equal. Now we can think of the drawbacks of Rutherford, so that his model was modified by Niels Bohr, who suggested the atom as a planetary system. So what are the drawbacks of the Rutherford atom model? First one, an electron revolving around the nucleus gets accelerated towards the nucleus. Now what happens to an accelerated charged particle? An accelerated charged particle must emit energy or radiation, and it will lose its energy. So the electrons, by Rutherford's atom model, he was saying that the electrons are revolving around the nucleus. Since electrons are charged particle, when they get accelerated, they will emit a radiation and will lose energy. So the electrons in an atom must continuously emit radiation and lose energy. So what happens to such an electron which loses its energy? We can see here. See, the electron in a circular orbit is not expected to be stable. Any particle in a circular orbit would undergo acceleration, and during acceleration these charged particles would emit radiation having energy h nu. So here you can see that this electron revolving in circular orbit will emit the radiation and will lose its energy. Thus the revolving electron would lose energy and finally will fall into the nucleus. If it is like that, will the atom be stable? No, isn't it? So the atom will not be stable if the electron is losing its energy when it is moving in a circular orbit. But we know that the atom is stable. So that was the first drawback of Rutherford atom model. He couldn't explain the nature of the electron or the energy related to an electron which is accelerated in a circular orbit. So because of this loose energy, the electron would slow down and will not be able to withstand the attraction of the nucleus. As a result, the electron should follow a spiral path and ultimately will fall into the nucleus. If it happens, the atom should collapse in about 10⁻⁸ seconds. But this doesn't happen. We know that the atoms are stable. This indicates that there is something wrong in Rutherford's nuclear model of atom. Now the second drawback is that the Rutherford model of atom does not say anything about the arrangement of electron in an atom. How the electrons are arranged? There is no answer to this question according to Rutherford's atom model. And it was Niels Bohr, a Danish physicist who studied in Rutherford laboratory, explained the spectrum of hydrogen atom and presented his own atomic model, and he was awarded the Nobel Prize in 1922. And according to him, in 1913, he explained atom is like planetary system with the electrons revolving around the nucleus like planets revolving around the sun. So let's see what's the Bohr model of atom. So the electrons revolves around the nucleus in definite energy levels called orbits or shells in an atom without radiating energy. So according to Bohr's atom model, the electrons are revolving in definite orbits with definite energy so that they are not radiating any electromagnetic energy. Second one, as long as the electron remains in a shell, it never gains or loses energy. So here you can see that the nucleus, positively charged nucleus is depicted here, and the electrons are revolving in the orbits outside, and each orbit is given a name, n equal to 1, n equal to 2 and n equal to 3. So whenever the electron is in this shell or orbit, the electron will never gain or lose energy. Now, when it will gain or lose energy? When there is a jumping of electrons from one energy level to another energy level. So the gain, here you can see that the gain or loss of energy occurs within the orbits only due to jumping of electrons from one energy level to another energy level. See, here you can see an electron in the n equal to 1 state or n equal to 1 shell. So whenever it gets an energy of h nu, it absorbs that energy and gets excited to the higher energy level, that is n is equal to 2. Similarly, an electron in n equal to 2 state never radiates energy. But since it is an unstable state, that means higher excited states are unstable states. So, in order to attain the stable state, that is a ground state n equal to 1, it will emit its extra energy, that is h nu energy is emitted and it will come back to the lower energy state. So when there is a jumping of electrons between energy levels, then only there will be gain or loss of energy. Otherwise, the electrons will not lose or gain energy when it is in a fixed shell or orbit. Now the fourth point, the electrons are revolving in a circular orbit, isn't it? So the electron will have an angular momentum. What is the angular momentum? That is mvr. And the angular momentum of the electron is an integral multiple of h by 2 pi. So here you can write it as mvr, which is equal to an integral multiple of h by 2 pi, that is n into h by 2 pi, where n gives you the number of shell or orbit, that is n is equal to 1, 2, 3, 4, etc. So angular momentum is an integral multiple of h by 2 pi. So that was the 4 postulates of Bohr's atom model, and based on these postulates we are going to derive the radius of an orbit, energy of the electron in an orbit, and also the wave number. So for that we are considering an atom. We are considering an atom having an electron moving around the nucleus, and this nucleus is having a charge Zd, where Z is the atomic number. And here we are considering m as small m as the mass of the electron, v as its velocity, and r as the radius of the orbit. So this electron having mass m, velocity v and radius r is revolving around the nucleus of charge Z into E. So what is the force of attraction between the nucleus and the electron? We know from Coulomb's law we can write it as Fc, that is the coulombic force of attraction, which is equal to 1 by 4 pi epsilon 0 q1 q2 by r square. Now what is the charge of electron? E. What is the charge of the nucleus? Zd. The distance between them is the orbital radius, that is r. So you can write Fc as Zd square by 4 pi epsilon 0 r square, with epsilon 0 as the permittivity constant, that is 8.84 into 10 raised to minus 12 coulomb square per Newton meter square. Now, so this is the coulombic force of attraction between nucleus and electron. Now the electron is moving in a circular orbit, isn't it? So what is the force there? Centrifugal force, or we can say that it to be the centripetal force acting on the electron. That is equal to mv square by r. And these two forces balance each other, so that we can equate both these equations and can simplify it and can find out the value of r, that is the radius of the orbit. It has Z e square by 4 pi epsilon 0 m e square. That is the radius of the electron in an orbit. Now, we know that according to Bohr's postulate, angular momentum is an integral multiple of h by 2 pi. So, from this you can write the velocity here and you can take the square. So, you will get v square, and you can substitute v square in this previous equation. Here you can substitute for v square and can finally write the equation for r. So that is equation for r, that is n square h square epsilon 0 by z e square into pi m. N square h square epsilon 0 by pi m e square into z. You can write this equation in terms of h cut also. What is h cut? H cut is h by 2 pi, isn't it? So you can write h as h cut into 2 pi. So you can write this expression for radius in terms of h cut also by substituting h as h cut into 2 pi. So that is the radius of the orbit. And we know that for hydrogen atom, the atomic number is 1, isn't it? So you can substitute z as 1 here and can find out r as n square h square epsilon 0 by pi m e square. Here you can see that epsilon 0, h, pi, m and e are all constants. So you can calculate that constant, or you can replace that constant with another variable, that is a0. So you can write r as n square into a0. And what is a0? a0 is a constant whose value is epsilon 0 h square by pi m e square. And this a0 is known as Bohr's radius. In your textbook, a0 is given as a suffix 0. So sometimes a0 is represented as a suffix 0, or you can represent it as a superscript 0. So a0 is the distance which is known as the Bohr's radius. Now you can calculate that Bohr's radius a0. Here a0 you can substitute all the constants and can find out the value as 0.53 angstrom. So you can conclude the radius as r is equal to n square into a0, with a0 is equal to 0.529 angstrom or simply 0.53 angstrom. So with this equation, with this last equation, Rn is equal to n square a0, you can find out the radii of all the orbits permitted by the Bohr's model. Only certain radii are allowed by the Bohr model. Since you can substitute n as 1, 2, 3, etc., isn't it? So substituting 1 you will get a0, substituting 2 you will get 4a0, substituting 3 you will get 9a0. That means only certain radii are allowed by the Bohr model, and that the radius of electron's orbit may be either a0, 4a0, 9a0, 16a0, etc. It can never have values like 3a0, 5.3a0, etc. So the radius of the electron can have specific values which are allowed by the Bohr's model as Rn is equal to n square into a0. See, here you can see the values of the several radius of orbits. When n is equal to 1, R1 is 0.53 angstrom, that is the Bohr radius, that is the minimum distance to the electron from the nucleus, which is known as Bohr radius. For n is equal to 2, you can have R2. For n is equal to 3, you can have R3. And for n equal to 4, you will get the radius of the orbit of an electron, which is in the n is equal to 4 shell. Now you can find out the energy of an electron in an orbit. We know that the energy, total energy, is the sum of kinetic energy and potential energy. So kinetic energy, you know that it is half mv square. And what is potential energy? Potential energy is 1 by 4 pi epsilon 0 q1 q2 by r. So 1 by 4 pi epsilon 0 q1 is Z into E, Q2 is minus E. So Z E square with a negative sign. So potential energy is minus Z E square by 4 pi epsilon 0. So that is expression for total energy. Here you can substitute for V and R from the previous slide. So from mv square, from the equation 1 we will get mv square and can substitute mv square for in the expression of kinetic energy, and you can simplify the total energy and you will get the total energy as En is equal to minus Ze square by 8 pi epsilon 0 R. That is the electron's energy in any orbit, minus Ze square divided by 8 pi epsilon 0 R. Now putting the value of R again, you can again simplify the energy equation and you will get it as minus Z square m e raised to 4 divided by 8 epsilon 0 square n square h square. Here also this expression can be written in h cut also. For that you have to substitute h as h cut into 2 pi. So you will get the expression in terms of h cut. So this is the general expression for the energy of an electron in the nth orbit. So from this expression you can calculate the energy of an electron in any orbit. And we know that we have calculated this for a nucleus having a charge Ze. So for hydrogen atom you can substitute Z as 1 and can find out the expression for energy as minus me raised to 4 by 8 epsilon 0 square h square n square. Again me raised to 4 by 8 epsilon 0 square h square is a constant. So you can substitute that value here, so that En is equal to that constant into 1 by n square joules. So here the energy is represented in joule, so that we got the value as En as minus k by n square, where k is 2.178 into 10 raised to minus 18. You can express this equation in terms of electron volt also. How? By using the conversion equation, 1 electron volt is equal to 1.6 into 10 raised to minus 19 joules. So here we got it in joules, isn't it? You can convert it into electron volt and you will get En as minus 13.6 electron volt by n square. I repeat, En is equal to minus 13.6 electron volt by n square. What does this equation mean? Similar to the radius equation, you can substitute n values and can find out the radii of different energy levels, isn't it? Here also, by substituting the value of n, you can get the values of energy, and only those values are only the permitted values or allowed values. That means the electron's energy is quantized. What is meant by quantization? Only certain energy values are possible. Which are that energy values? By substituting the values of n here. See, here you can see that for 1 mole of electron you can multiply it with the Avogadro number. So simply a calculation which helps you to find the energy of the electron in an orbit. See, here you can see that in terms of kilojoule per mole. Here we had calculated it with a joule per mole, and this is kilojoule per mole. And again calculating all the constant values, you got it as 13.315 by n square into kilojoule per mole, and you can substitute the n values here and can find out the energy values. So what does it mean? Energy can have only these much values. Only these much values of energy are possible, which is known as quantization. So the electron's energy is quantized similar to the radii of the energy levels. So in the lowest energy level means n is equal to 1. The electron has an energy, this much energy, kilojoule per mole, or you can represent it in electron volt also, that is minus 13.6 eV, with the radius R1 is equal to Bohr radius 0.53 angstrom. So this state is known as the ground state. So the minimum value of n, that is the lower energy state, that is n is equal to 1, you can get the value of energy, that is E1, which is minus 13.6 electron volt, and the radius, which is known as the Bohr radius 0.53 angstrom. This energy state is known as the ground state. And all other states, that is n is equal to 2, n equal to 3, n equal to 4 are known as excited state. So the first energy level when n is equal to 1 is called the ground state of hydrogen atom, and all other states are called excited states. So here you can see the picture from which you can see the energies are increasing, and the ground level is known as n is equal to 1 state, which is the ground state, where E1 is equal to minus 13.315 kilojoule per mole, or it is simply minus 13.6 electron volt. Now from n is equal to 2 state, all the states are excited states. All other states are excited states. N equal to 2, again you can calculate E2 as minus 13.6 eV by n square, that is minus 13.6 eV by 4, and it is minus 3.40 electron volt. Similarly, you can calculate the values of all other excited states with the help of equation En is equal to minus 13.6 eV by n square. Now we are going to calculate the frequency of radiation emitted by an electron. We already told that whenever the electron is in the orbit, it is stable, and when it makes a jump from one energy level to another energy level, there occurs the emission or absorption of radiation. And here we are going to calculate the frequency of the radiation emitted by an electron. So we have already the equation of energy with us, and you can substitute n as 1 and can find out E1, and n as 2 and can find out the expression for E2. Now what is delta E? That is the difference in energy. So you can calculate it as E2 minus E1. Isn't it? So you can calculate and you can find out the expression for delta E, and in the case of hydrogen atom we know that Z is equal to 1. Again the constant is given as a factor 2.18 into 10 raised to minus 18 into 1 by n1 square minus 1 by n2 square. Now according to Planck's quantum theory, which we had already studied in the black body radiation, we know that the energy associated with transition is equal to h nu. So the energy here we got it as delta E is equivalent to h nu. So from that you can calculate the frequency nu, isn't it? So nu is equal to me raised to 4 by 8 epsilon 0 h cube into 1 by n1 square minus 1 by n2 square. So this is frequency, and the unit of frequency is hertz. So this much hertz or cycles per second. And you can calculate this constant, and it is obtained as 3.29 into 10 raised to 15 into 1 by n1 square minus 1 by n2 square. Now from this you can calculate the wave number also. So frequency is equal to C into wave number. So you can substitute again nu as C into nu bar and can find out the expression for nu bar. I repeat, here we got an expression for nu, and nu is related to nu bar, that is wave number, as C into nu bar. So you can substitute nu as nu bar into C and can find out the value of nu bar. Nu bar is wave number, which is equal to 1 by lambda. So again we took the constant, putting all the constants together, and that constant is given a factor called Rydberg's constant R, which is equal to 1.09678 into 10 raised to 7 meter inverse. So that nu bar is equal to 1 by lambda is equal to R into 1 by n1 square minus 1 by n2 square. See, we had took the derivation from the energy values, isn't it? E1 and E2. See, from that we had started the derivation and we found the energy difference. We calculated it with equated it with the Planck's quantum theory, so that delta E is equal to h nu. From that we got the expression for nu, and substituting nu as a C into nu bar, where nu bar is the wave number, we got the expression for nu bar as R into 1 by n1 square minus 1 by n2 square, where R is the Rydberg constant. Now we can, so with the help of Bohr atom model, we calculated the radius of an electron in an orbit, energy of an electron in an orbit, the frequency of the emitted radiation when an electron jumps from one state to another, and also the corresponding wave number, isn't it? Now we can think about the defects of the Bohr atomic model. According to Bohr, the radiation results when an electron jumps from one energy orbit to another energy orbit. But he didn't explain how this radiation occurs. He couldn't explain how the electrons emit radiation when it jumps from one energy orbit to another. Second one, Bohr's theory explained the existence of various lines in hydrogen spectrum, but it predicted that only a series of lines exist. So whenever an electron jumps from one state to another, there is a frequency related with that transition. That frequency can be plotted or can be seen in its spectrum. So if we are studying hydrogen, we can see several lines. See here in the slide also you can see several lines, isn't it? So that several lines will be there in hydrogen spectrum. And this spectral lines that had been thought to be a single line was actually a collection of several lines very close to each other. See here you can see a red line, isn't it? But watching closely you can see several red lines, isn't it? So Bohr's theory failed to explain the presence of several lines instead of a single line in a hydrogen spectrum. Now third failure, Bohr's theory successfully explained the observed spectra for hydrogen atom and also similar ions. Similar ions means we know that hydrogen atom consists of only one electron, isn't it? So one electron atoms can be studied with the help of Bohr's theory. One electron atom means here we know that helium has having 2 electrons. Helium 1 plus means 1 electron is gone. So now the helium is He1 plus. That means it contains only 1 electron. Similar in the case of lithium, beryllium also. These all contain only 1 electron. So Bohr's theory successfully explained the atoms that contain only 1 electron. But it cannot explain the spectra for polyelectron atoms. That means the atoms that contain more than 1 electrons cannot be explained with the help of Bohr's atom model. If a substance gives emission spectrum, when it is placed in a magnetic field, the lines of the spectrum get split into a number of closely spaced lines. This phenomenon is known as Zeeman effect. I repeat, whenever we take a spectrum, here you can see a spectrum, isn't it? Think of this to be a spectrum of any atom. And when this spectrum is taken with no magnetic field, there is only one spectral line. But whenever this spectrum is taken again with the magnetic field, the spectral line splits into 2 or splits into 3. And this phenomenon of splitting of spectral lines in the presence of magnetic field is called Zeeman effect. I repeat, the splitting of spectral lines in the presence of magnetic field is called Zeeman effect. And Bohr failed to explain the Zeeman effect. That was the fourth drawback. Now another phenomenon which is known as Stark effect. In the presence of electric field, the lines of spectrum gets split up into a number of closely spaced lines. So this phenomenon is known as Stark effect, similar to the effect Zeeman effect in the presence of magnetic field. Here the lines of the spectrum get split into a number of closely spaced lines in the presence of electric field. So this Stark effect was not explained by Bohr. Sixth drawback, Bohr suggested circular orbits of electron around the nucleus of hydrogen atom. Later he modified it as the planetary motion, in which we can consider planets, the picture of a planet moving around the sun as that of an electrons moving around the nucleus. But later it was proved that the motion of electron is not in a single plane, but it takes place in three-dimensional space. So whenever we think of an nucleus and electron, we will draw like this: a positively charged nucleus here surrounded by an electron in a plane. So the electron is moving like this, isn't it? But the picture is not like that. The electron can have three-dimensional motions. So this picture was not explained by Bohr. Seventh drawback, Bohr assumes that an electron in an atom is located at a definite distance from the nucleus and it is revolving around it with a definite velocity, so that it has a fixed momentum, isn't it? The electron is revolving around the nucleus with a fixed velocity, so that it will have a fixed momentum. But this idea is not in agreement with the Heisenberg uncertainty principle. What is uncertainty principle? Uncertainty principle states that it is impossible to determine the exact position and momentum of a particle simultaneously with certainty. That means if the particle is moving, we cannot accurately measure its position and momentum simultaneously. But Bohr tells us that the electron is revolving in a fixed orbit with fixed velocity. That means it is having a fixed momentum, isn't it? But according to uncertainty principle, it is impossible to determine the position and momentum simultaneously. So this also form one of the drawbacks of Bohr's atom model. So in this class, we started with Rutherford's atom model, the drawbacks of Rutherford's atom model. From that, Bohr atom model, in which Bohr considered an atom as a planetary system, and we also derived the equations for the radius, energy, frequency and wave number of an electron in an orbit. Also for any atom, we can calculate it for any atom with the help of the Z in the equation. And also we saw the different drawbacks of the Bohr atom model. I think the session is clear to you. Thank you.